Hi, everybody, and welcome to our webinar on advanced material solutions for co-packaged optics. This is the third in a series of webinars sponsored by DuPont Silicon Valley Technology Center and the Consortium for Onboard Optics, or COBO. So I'm really happy to be doing this topic. I think it's really interesting to talk about the material science because it really takes us back to the first principles of engineering. We can just imagine what data communications are going to be like in 5 years or 10 years. Faster data rates, more bandwidth, denser data centers, and to get there, material science is really going to be key. So today we have two of the leading companies in advanced materials, that's SABIC and DuPont. Our first guest is Peter Johnson of SABIC, who has a presentation on the development opportunities for thermoplastic optical integration into co-packaged applications. Our second guest is Dr. Jake Ju, who leads the Optoelectronics group at DuPont. So with that, let's kick it off. Peter?
Thank you. So I'm Peter Johnson from SABIC, and I'll be talking about some thermoplastic opportunities for optical integration into co-packaged applications. And so just to briefly for a moment go into who SABIC is in case you don't know. It's a global leader in chemicals. We make a variety of different, both just chemicals, polymers, and other types of materials that go into a variety of different applications across the globe. And the company is based in Riyadh, but it is a global operation. I'm currently working from home in Mount Vernon, Indiana, near one of our polymer plants that produces materials. And so we sell a wide variety of products and generate a new variety of products each year to meet customer needs. And just to briefly go through it, again, we have a variety of different businesses. The petrochemical side is mainly for commodity plastics and chemicals. The specialties business is more for specialty engineered thermoplastics, where there's a lot of different custom requirements required to get a material that actually meets the application end use. And then there's also businesses in agri-nutrients and metals. But really, to talk about what we're here for is the specialties business, which is mainly focused on being a material supplier. And our resins are sold and converted into a variety of different applications, into a variety of different fields as well. So into electronics, automotive reflectors for mobility, industrial applications. The consumer electronics, we sell actually both the polycarbonate that goes into the lenses and the actual Ultem resin that goes into the glasses frames themselves. So like the ones I'm wearing, these are Ultem frames with polycarbonate lenses. And really the focus that we learned about the data center applications out of the Ultem 1010 resin, where we were making material that was then being used as an injection molded thermoplastic lens. And this was actually about 20 years back for TOSA and ROSA modules. And a large variety of our materials are used in other connector components as well. And so the focus of this talk is really to talk about the optical side as well as the connector side of things, and where we see our materials going in the future and what we hear from customers on what the demands are in the future. And so the core of it, I think, comes down to a robust optical design. So this comes into two different factors. One is the reduction of the signal loss during assembly. And this is where it could be as you move to a co-packaged optic and you start to need solder reflow assembly, that there's no deformation as you go through that lead-free solder reflow temperature of 260 degrees C. It could also be something where we're trying to improve the alignment or placement of the fiber optics themselves to make sure that they align properly with your laser source or your photodiode. And then, of course, there's always something on the reduced connector size, because as you start to concentrate more and more fibers, you also need to start concentrating that in the connector as well. Once you've actually made the part, though, the key component is maintaining that optical signal. We can't have it break once you fully assembled the component, because that might risk actually, having the component need to be tossed. So we want to maintain that through dimensional tolerances, even in single mode operations, have aging standards and material performance that's really robust, and then low impact assembly methods. So the more we can pre-assemble or actually simplify the process down, the better yield and the more robust the connector will be in the end. So as SABIC looks at it, we're focused really on material properties. So what we want to do is improve dimensional stability through any different aspects that we see as we look at this sort of co-packaged optic space here. And then demonstrate design capabilities that give us flexibility and increase part integration, and then the performance evaluation of it for aging, chemical exposure, other things that potentially could come up along the way, and how our material would respond to that. So it's not a hidden unknown as you start developing programs. And when we talk about thermoplastics in comparison to, say, glass or epoxy materials, the real key consideration is design freedom. When you do an injection molded material, you're melting the plastic down, injecting it into a mold, that mold cools it down, and then it releases it out. By doing so, you can make a variety of complex different shapes and designs, and this allows you to simplify a lot of things down. This part here that we're showing is actually XTEM lenses, 2 different lenses, along with an actual housing body, all done in one single shot. So we can integrate all of these different components into one single design. And once you do that, you can make millions of these at a time. So it allows for that precise manufacturing at very large build numbers. And that's one of the advantages that thermoplastic materials really provide in this application space. And so we're going to go through some of those applications in terms of both the connector at the faceplate and the connector that would be closer to the onboard optics. And the first one we just want to cover is that with the connector components, really it's high reliability. You don't want the fiber optic cable that you've run for a very long distance in the data center to break. And so there's multiple different options available. The requested properties here are really high stiffness and strength. So you want a material that's robust and can handle abuse, because if you need to switch something out, you're probably not going to spend a huge amount of time being very precise and gentle with the component itself. As we go to, again, higher and higher fiber densities, you need to make those fine features even smaller or even more densely packed while maintaining that precise alignment. And so there's multiple options available on the market. They sort of break down into the amorphous resin side where Ultim lies, and then there's the semi-crystalline side where other different materials reside. And it's really a balance of how you can replicate the part along with the dimensional stability that you get at the end. And what we're showing here is coefficient of thermal expansion at the bottom. In the case of PEI, which would be an amorphous resin, the Ultim resin in particular, the coefficient pretty much stays constant across this temperature range we're showing. With something equivalent, say like a PPS, once you start reaching certain temperatures, it can start deviating. So it really depends on what your operating window is and how the design actually works. If you need something that's more robust, you might have to go one way or another. It really just depends on what you're looking for in the end. The second thing that we wanted to actually focus on was building new chemistry, because there were certain limitations that we've seen with Ultim. And we built this XTEM resin portfolio, and the whole goal of it is to maintain stiffness and dimensional stability through lead-free solder reflow conditions. It's still based on the Ultim chemistry process. And what we were mainly focused on was getting something that could meet 260 degrees C peak reflow temperature. And how we were looking at this was storage modulus is sort of a reference of how stiff something is. So if you're trying to, say, bend a part and it actually, how stiff was it to that bending motion? When we get up to about 200 degrees C with Ultim will start having some softness and it will start actually deforming. With these XTEM materials, we can push it up to and beyond 260 degrees C for the peak reflow temperature that we know occurs in lead-free soldering. And we were able to validate these on test plaques. And test plaques aren't necessarily the best thing ever. And we really wanted a realistic optical design to complete the validation. So we started to work with Nailix in Japan. They're actually working with an OEM on multi-mode onboard optics, co-packaged optics. It depends on how you really want to define the borderline for what they're doing. But they designed this connector using the XTEM NG resin series. They took all of the optical properties and data that we had for how you mold it, how you process it, what the performance would be like in the end, and built this component that you see here, which is actually fairly small. It's only about 4 by 9 millimeters, but it contains a lot of different individual components in it. You have 4 receive and 4 transmit lenses on the front with an empty ferrule connection. There's 4 lenses on the bottom as well for each side. And then there's the internal reflective mirror that you can see on this. So it will take the light from the side and reflect it down onto the PCB board. And the whole goal here was to have something that maintained dimensional stability, so you could put this on, align everything, and then just sell that package pre-lined with optics, and you just had to snap in the connector and you're good to go. And so the results that we got from that were actually pretty great. The dimensional stability, how we were measuring it, was based on alignment spacing of these various different components. And this is just showing for 260 degrees C reflow, 3 passes. the dimensional change of these various, say, lens spaces, empty ferrule connection spaces, a variety of different conditions. And you can see they mostly change by less than a micron, which is a very good result for a resin to go from effectively room temperature to 260 and back over and over again, and it's still remaining dimensionally tolerant through all of those processes. We've also done this where we connect it to the optics to prove the validation, and we see that there's a fairly low change in the signal loss even through that entire reflow set. We don't see any visual deflects and anything like that. And we're currently going through all the aging and long-term performance studies. That, of course, takes a lot longer. And we want to make sure that this is robust for a very long time, because while it is based on Ultem resin, we still want to make sure that everyone's comfortable with how the material performs. And we're going to show some of that data at the end. And so with this, we have a material now that actually is IR transparent and solder reflow capable that we can injection mold. And in reality, to make this part out of something that would actually be glass would be a very involved, complicated part, because you're including potentially up to maybe like 8 different to 9 different components to actually do that out of a mix of metal, ceramic, and glass. The second thing that we get feedback on is single mode optics. So having single mode transmit and receive optics really require glass-like properties. The requested properties here, of course, are still having that IR transparency, but it's also having this low coefficient of thermal expansion. So when we're talking 10 to 20 parts per million per degree C, it's more that the PCB board or the silicon chip, if this is silicon photonics, will expand by that rate. So the optics themselves also need to align with that coefficient of thermal expansion. And what that can do is it can cause a misalignment if we would just use the standard thermoplastic like Ultem that we currently have. And so our options, again, this is experimental in a lot of cases, but in the field, there's generally 2 options. One is to make a new polymer. That's really long development time. It also is something where you have to sort of change the chemistry, which has a long lead time in terms of regulatory performance. The main core problem, though, as we've looked at the field, is that a lot of the research is focused on foldable electronics or OLEDs. In reality, that's a very large market, and there's a very large focus on making a film like that. But once you've made a film like that, it's not an injection moldable plastic. It is something where you're trying to make a film, set it, and almost cure it like a thermoset material. So it's really sort of outside of the scope of what you could do with a plastic optic, where we're talking in these cases. In the case of blends, it's a much faster speed to market. We've actually internally done some developmental work trying to make something that actually is lower CTE, but still IR transparent. It's really a balance of the properties. You need to lower CTE, maintain optics and surface quality. And that's where the tailoring of the design and what your tolerances are for various signal loss really come into play. So there's options available. We've done some internal testing, but are still going through all the aging evaluation. But it's something that is capable. It's just a question of what are you willing to trade off? And of course, we believe that we can get to a better performance in the future. It just will take a longer time. And so with this, this sort of covers the main uses of thermoplastic optics in the data center space, especially within when we constrain to within the box itself. And what we wanted to go through next was more design capabilities. So if you actually want to implement this resin, how would you go about doing so? And so with that, the first thing, of course, like we talked about with the design that Nailx produced for us, was the optical performance. So we provided percent transmission, refractive index, DNDT, stress optical coefficient, a variety of different data to them so they could make sure that they had the best possible design. And what we're showing here is both the XDEM resin series, the XH1015 and the NGE series. But these actual parameters for a lot of these different resins, at least from the SABIC side of things, we've been putting them into Zemax Optics Studio to make sure that they're just commonly available. We also just have the standard test parts if you want to confirm them, of course. But really, this is the core of what you need before you actually go into the modeling of the component. And how that works is we've actually gone through and made sure that we can do it at this scale. When you're micromolding a part, so this part here is 0.3 millimeters thick. So we're trying to go down to very thin components, make sure that the actual design and mold flow simulations actually work at that level, and that we can optimize flow and stress and birefringence. Because once you get down to that thin of a part, you're pushing material at very, very small dimensions, and we wanted to make sure the model optimized it correctly. And so with this, we're able to actually produce parts. We were able to make this part where we have this 4x3 lens array to the replication size and dimensions that we wanted. and also actually go through this and make a 3D surface image of the component to make sure that we're replicating the lens, that there's no sort of deviation in the shape and size of it. And this was something that we wanted to do internally to make sure that we could support customers as they're developing components. The other things that we wanted to talk about was more of how you do this part integration. It's great to say that you can mix these two materials together or do these complex components, but it's actually quite hard to know the processes we go through. So we wanted to cover some of those details. And in this case, we're talking about diffractive optics, where we're just using DVD replication techniques. It actually even goes back to the CD replication techniques, where you're trying to make just very small surface features for diffractive optics. And what we produced here was actually injection molded optics at about 600 nanometers of height. And those are actually about 3 millimeter square pillars on the bottom left corner. And what that does is when you shine light through it, you can get the diffractive pattern. This can be more useful in sensor applications than necessarily in the optics field, where you're trying to focus light. But it's something to consider, especially if you're trying to get light from one surface to another without necessarily having any sort of specific lens to actually collimate the light. The second thing that we talk about is always reflective and anti-reflective coatings. We've been able to demonstrate both metallization of a surface, like we're showing here on this part where we're making actually alignment holes for a larger optical component, and then anti-reflective coatings where we can boost the system usually about 4 to 8% in terms of percent transmission. And those types of things are something that we really do to make sure that if you need to boost the light signal or manipulate the light, there's options available for what you need in terms of capability. The second part that we showed, of course, was this component here. It's now zoomed in. This is the XTEM lenses with the actual black subassembly around it. That black subassembly was mainly overmolded onto this component through a two-shot injection where you first inject the XTEM and then you inject the other component. That was done to make sure that you block all the light. So that photodiode and the laser, we didn't want any backscattering between one lens to another to actually interfere with our signal. So they built the entire overmolded component around it to block all that light. It also helps with, say, doing a rigid alignment or mounting. Once you put a very stiff material around that XTEM lens, you're really not going to be able to deform it through a lot of manipulation methods. It allows you to do a lot more easy of assembly and gluing process. The version we show internally here actually has, again, some pattern on this center surface and a solid mounting ring, which we use sort of as our standard alignment tool. And we do that, of course, internally just to make sure it works, but it also just helps us to actually have that rigid component that is sort of supported by the base optics that we need. And that allows us a lot more flexibility in terms of handling and manipulation that we really don't see if you just do it out of a single shot. And then the final thing was the PCB assembly techniques. We've done the epoxy and silicone testing. The few things to consider here is that if we're gluing, say, on this box on the outer edge, we really aren't super concerned with the transparency of the material. In the case of, say, the material when we're going through and we're actually trying to glue the lens directly on the board, we might care about transparency, we might care about shear testing, or just the dispensing of it. So it really depends, but we've tried to sort of cover our bases in terms of what we need for assembling the materials out into the components themselves. And then the final thing that I just sort of wanted to cover was, again, aging processes. So when we're talking about this material, it's great if we can make it, but if it doesn't last for, a long enough time, it's effectively useless. And from what we've tested so far, the XTEM series is comparable to the Ultem resins that have been used for 20 plus years now in these optical components. We haven't seen any significant change in light transmission, visual color change, haze, or void formation. What we're showing on the right here is Ultem 1010 versus XTEM NGE resin series. And in general, we're not seeing a huge difference or delta as we sort of build up in time. And these parts are still going, of course. We're going to try to go as long as we are physically able to make sure that we get validation out to as long as possible. We're also doing some testing that is sort of preliminary work on sort of water immersion and heat aging, because we're concerned as we get closer and closer to that co-packaged optic on whether or not there's a heat loss or a differential in temperature that we need to be concerned with. So we're just trying to make sure that every base is covered before we actually go and implement this part in the future. The second thing that we do is we do have our own in-house solder reflow for proof of concept testing. So when we say we have done 3 passes at 260 degrees C, we've done it internally at various moisture sensitivity levels. The nice thing that we've learned about having our own machine is that we can vary the solder reflow profiles. We can make them short or long. We can ramp up the temperature. We can just sort of let it sit and hold at 260 degrees C just to abuse it and make sure that there's really no failures going on. And this is something that when customers have asked for it, we've let them use our tool, because to us, right, it's just making sure our part actually works through the performance characteristics we say it can. And we've done that through, rebake simulation profiles as well, just to make sure that all of these components mix well together. We don't want to be the specialized components. We just sort of want to be a standard component on the part. And with an amorphous resin going through solder reflow, it's really difficult to believe that you could actually, get a part to actually be produced and molded and assembled. And that's really what we've been able to do here. And so we wanted to make sure that we had as much data as possible to really show that effect. And so I hope with this, I just sort of showed you a bit about what we have in the thermoplastic space. On the new material side, again, this is part of our introduction of the XTEM NG resin series, where we have materials now that can do lead-free solder reflow. And then on the low CTE side, there's really a big demand for that low single mode type of optic. And that's something where there's development work ongoing internally with us, and some other materials have been developed and proposed as well to do that sort of technology. On the design capabilities, we really just wanted to show the complexity in design that you could actually prove out with just a thermoplastic lens. In a lot of cases, people think it's just you're trying to replicate a hemispherical glass lens, but you can do so much more. You can make diffractive optics, you can mix materials, you can put on different coatings and surfaces that actually really change the fundamental behavior of what that resin can do. And with all of that, of course, though, we needed to make sure that the validation tools and data sets were there to actually do that reliability testing. So from our perspective on co-packaged optics, what we've seen is that the dimensionally stable, single mode thermoplastic optic is sort of the holy grail in terms of what we need to design towards, which could be solder reflow assembled. And we're trying to get to that point to make sure that we have all those components in place to give the real opportunity that we see of actually putting lenses on that co-packaged optic and get the integration and assembly down to the scale that's needed for these high throughput and high fiber loaded switch networks. And so with that, I just wanted to thank you all for your attention. And so this is just where we can contact ourselves. I would like to thank DuPont for actually putting in all the network infrastructure for this meeting. And with that, I'll let it switch over to Jake, and he can give the interesting DuPont talk that I've seen. Thanks.
So thank you everyone for joining the call. What I'm going to actually present today is just overall general outline of our corporate itself, and then see what are really the critical material challenges that comes from the data center, and what are some of the new opportunity for as a material companies to be able to deliver some of the new options to accelerate some of the development in next data centers. And then lastly, I'll cover a small amount of some of the standardization that can potentially help this industry to move forward even faster. A little bit of introduction about the DuPont itself. Some of you know as a DuPont is a specialty company, but recently we went through with the merger and the split between Heritage Dow and Heritage DuPont, and then reshuffle the portfolio to make sure that the current DuPont actually has a very specific target in mind to actually accelerate some of those specialty chemical companies. We have 5 different segments in the business unit: nutrition, bioscience, transportation, industrials, safety constructions, electronics and imaging, and non-core. So with respect to the context of co-packaged optics, the business units, what I'm going to talk about is actually electronics and imaging business. We cover a lot of different material that goes from the bottom up, from the wafer fabrication all the way up to the chip packaging, and even the module level or system level displays and other units as well. So within electronic imaging, what we do is really just creating the value chain, the material that can actually transform, starting from the silicon substrate all the way to the system manufacturing. We cover photoresist, we do electroplating on material development, CMP pad for polishing, going up to the chip packaging, and as well as display materials and film goes into many different value chains as well. If you think about more specific to packaging and optics and board level, there are multiple different levels of the material exist. We cover the wafer fabrication in 5 nanometer node dimension photoresist cleaning materials. We also cover the material for electroplating as well as dielectric material that goes into fan-in, fan-out packaging level. If you go to larger scale into BO or back end of line, in millimeter scale, we also do the electroplating materials. We also cover some of the thermal material that can be used for assembly material as well. So based on different types of material, what our company actually covers, we start looking into the optics as one of the strategy for us to be able to making a significant impact to actually making a progress for helping out the society in terms of the data center aspect. So I'll change the topic slightly about just more starting from the more the general. What are really the challenges what the data center has? I assume this audience already knows about the background, but just give a brief overview. What we are talking about as a next-gen switch or the server system, one of the critical challenges what we have is really trying to increase the bandwidth, but at the same footprint, at the same time with a higher energy efficiency. The way what we see it is that currently you have a transceiver on the faceplate of the switch ASIC, and from there to go to ASIC, there's a copper line going in. And one of the challenge if you wanted to going into higher data bandwidth in the per switch, you really wanted to actually make sure that one unit really has the same energy consumption level or the cooling system electrical power. The one on the left bottom table, what it shows is one of the example of what Facebook from James actually presented from OFC this year, is that to be able to get to the deliverable what the market is looking for the server system, they wanted to get at least more than 5 times higher energy efficiency in terms of picojoule per bits in the data. And that's why where the co-packaged optics as well as onboard optics, the idea came in. So pulling those optical line from faceplate of the switch system very close to AC, that will allow the copper line loss converted with the optical, that will be a minimal loss in terms of optical fiber, that will enable overall energy consumption to be lower and then lower the cooling power needed and so forth. And indeed, some of the simulation or the modeling that is suggested that co-packaged optics will really be able to reduce overall surges power consumption up to roughly about 80%, but that with the caveat with a specific condition and design as such. And this one is one of the driving force for the overall market direction, and the light counting, one of the company actually provided the expectation that these optical chiplets or co-packaged optics or COBO will probably just giving an opportunity for us to ramp up some of the markets within 2023 as a starting point. So with all this great news, one of the challenges what we see is that there are not that many materials that will be able to deliver as of now in terms of performance, or not even be standardized. There are many different optical materials, as Sabi commented about some of the thermoplastics as connector parts, but there are optical waveguides, refractive index material, adhesive that also require some of the thermal requirement. There are dielectric material that might also be needed, not just the optics, but dielectric parts, and as well as a thermal management material as well. If you watch the last COBO webcast from Alexander from IBM, you probably have seen there are many different ways to integrate co-packaged optics. The one that I show in here is just 2 examples. The one on the top shows a cross-section of the simplified schematic. Then you have a PCB board, you have ASIC chip with the BGA with assembled, and there's a silicon photonic chip at the center. That's what we call it PIC, photonic integrated chip. There's optical fiber and there's a connector. So if the photonic chip has a V groove in the wet etch process, and then you assemble this single mode fiber, and then this one is a passive alignment. It has a lower profile than grating coupling, so that gives a benefit. And also assembly complexity is a little bit low, so this one is beneficial. The one on the bottom is another example of what you can also use it as an intermediary polymer waveguide between silicon photonic chip and outside of the world, single mode fiber. one of the challenges in the V group of fiber attach is that there's a limitation how dense you want it to put the optical fiber. You have a physical optical fiber in the outside world that has a dimension, single mode fiber, a few hundred micron. And if you have the silicon photonic chip has a die size that you want it to integrate multiple different lines, then there's a limitation footprint. That's where this optical line with the polymer waveguide can actually densify those outcoupled single mode fiber incoupled into the chip. So this one, you can think of it as optical fan-in or fan-out option to integrate. So this one is a slightly different option for integration. So as you can see, there are many different options what you can consider. And the question for the material supplier is that which direction the market is heading or the industry is heading. So how we can help the industry to accelerate the development. There are, even at conventional transceiver cross-section, there are so many different types of materials. You have a waveguide material, whether in the silicon level. You have optical fibers as well. You have lens material that actually focusing the light or disperse the light. You have optical adhesive materials and thermal seals, thermal materials, some of the metal layers as dielectric materials. So I'll try to go over maybe just one by one briefly, trying to share some of the basic principles, what kind of parameter that is required, how the material companies really develop or consider that one as an option to actually make it better performing materials. As I mentioned before, one of the examples is polymer waveguides. So if you wanted to have a polymer waveguide, one of the key criteria what you want is really the lower insertion loss. You have input of the light, you want it to have a minimum loss in the system level polymer waveguide and go into silicon waveguide and then go to the chip. Insertion loss is comprised of coupling loss that goes between a fiber to waveguide or waveguide to waveguide. That is defined by the refractive index difference between fiberglass to air to waveguide or index matching fluid, as well as end phase profile. You also have a propagation loss. That is really core material property. If the material absorbs a single mode waveguide 1310 nanometers and a high absorption wavelengths, then that will actually end up being a high loss. Same goes for scattering. If the waveguide has some of the surface roughness within the pattern structures, you may end up leaking the light. So based on this just a basic fundamental, what the company like DuPont, what we are doing is trying to identify the material that has the lowest absorption at 1310 nanometer for single mode or even 850 for multi-mode. And we also need to tune the refractive index based on the material composition to meet the target requirement. We also need to make sure that these lines or photo pattern structures are consistent each other with the whole area. And also, it also needs to withstand all the sort of reflow as what we would expect with the other processing that needs to be going through. And that will turn into some of the fundamentals, right? So you need to make sure that this 1310 nanometers absorption mostly coming from molecular vibration or carbon hydrogen or OH groups. Consider whether we wanted to put aromatic structure or not to having the more rigid structures, cross-sectional densities, as well as water uptake, because once you have a water, that can actually increase absorption wavelengths at 1310 as well. DuPont has been actually working on this field, not necessarily in optics, but in general in these types of material quite some time. We actually worked on benzocyclobutane type material, a photopatternable material called the cyclotene, and we use this one as one of the example of utilization for this photonic integrations. Cyclotene material 6505, we were able to demonstrate the material itself has low loss, about 0.3 dB at 1310 nanometers. And at the system level with the waveform level waveguide we fabricated so far has a roughly 0.5 dB. And it's rock solid at even at high temperature, total reflow condition as well. We can also change some of the clad formulation to adjust the refractive index based on customer's requirement. We also see the DNDT, the temperature-dependent refractive index is critical because that can also change the coupling behavior. And then that is consistent each other with respect to broader range of the temperature, meaning that it'll still guide through with a single mode as necessary. And the fabrication perspective, we are able to also demonstrate up to 5 microns around the ranges and generally make it about 8 to 10 micron range. with all the fabrication and also modeling, and to be able to deliver the custom design per customer's interest, and then trying to work along with the customer to define the parameters and be able to reformulate as necessary. So I covered the optics, but there's another thing. So if in terms of electrical signals, once you have a copper line, ASIC chip in signal, or even PCB board, copper line will also have inherent loss coming from conductor loss and dielectric loss. Once you go into the higher frequency or high speed, you start to have more portion coming from dielectric loss, because conductor loss is proportional to root square of the frequency, whereas in dielectric loss is proportional to frequencies. So especially in 5G application, not necessarily in data center, 5G application in the base station and others, a lot of people have been working on to making the material, dielectric material, that has a lower decay and DF, dielectric constant, as well as dissipation factors. That comes from the backbone molecule design that actually delivers what kind of properties, what you can get. And sometimes they also add some types of fillers to change some of the behavior as well. And as well as this electrical behavior, you also wanted to make sure that the mechanical stabilities are in place and then matching the CTE properties. In certain cases, you also wanted to have the material that is photo-patternable if needed. And in certain conditions, you also wanted to have different temperature and curing and so forth. And of course, water uptake is also important, because water will eventually increase the decay as well. So we, as I mentioned before, we have basics of cyclotron types of material, PCB material. We have been working on revising those materials from APT group in electronic imaging to see if there's some of the change in polymer backbone, as well as some of the photo package will be able to deliver the property what we were looking for. So we were able to actually develop customized material based on basic fundamental understanding we had with the BCB, and then based on that one, we were able to get the DF value at 20 gigahertz, less than 0.03, as well as dielectric constant less than 2.7 as well. One of the benefits in these types of material, what we actually found out was that the material itself is based on diene chemistry, so meaning that what kind of curing temperature you run, depending on the condition, DF actually doesn't change compared to some types of different types, acyl epoxy or photo polyimide that actually has a different curing condition that may end up delivering the different DF values. This one also have good photodielectric patterning capabilities that can be used for eyeline stepper or mask aligner as well. So based on these types of just a general chemistry, you can imagine you can use this one for photodielectric in specific pattern design. We worked with the Georgia Tech about a few years ago in terms of electro-optical transceiver design with the Corning glass structures. We were able to actually create the lens structures by different types of curing conditions. We are also making turning mirrors to actually reflect the light, then in-couple and out-couple as well. You can also change the material properties to actually having dry film to be able to use for the integration as well. So, as I mentioned, they're optical material, but that can also be used in dielectric material, or sometimes we target it for dielectric material per specific needs. That can also be for the optical materials. This one is a somewhat similar to what Sabic mentioned. Whenever we wanted to assemble the material into co-packaged optics, there is of course there's a fiber, and there is either polymer waveguide or something that needs to be fixed, or that needs to be coupled each other. And to be able to couple that one, you need some types of material, unless you just want to have an air material that will be able to actually guide the light, or even assemble those fiber with adhesive that has a right refractive index, because if it's not, you can leak out the light or trap the light. We have been working in these types of field at the discovery project internally to see some of the changes in the material backbone of the property that can actually enable the adjustment of refractive index. Initially, we worked on these types of material for display application, and as well as the sensor application, because they actually need some types of lens material. We were able to tune the refractive index and high refractive index to low refractive index based on the polymer structures, instead of adding different types of filler, because the filler can provide different variation in refractive index. but that can also come with a cost that can eventually scatter. That is potentially an issue for, at least for the optical data center aspect. Lastly, thermal management can certainly be an issue. I mentioned before the co-packaged optics, you end up making the optical fiber closer to the system, so energy efficiency is better. So the cooling power may not be as needed as expected, but if you think about it, you end up increasing the capacity of data bandwidth 10 times more, starting from 12 terabits all the way up to 102 terabits. You end up still densifying all those data transfer within the smaller footprint. That's why where the thermal interface materials or the thermal management solutions are getting more and more attention once you go into the next generation switch. So I will not go into too much detail on this topic, but our company has been focusing on trying to develop the TIM1 material meets the 6 watt per meter Kelvin. But there are some other development in progress with a higher 10 watt or above meter Kelvin with the material development with different approaches to address some of the concerns what the market is currently asking for. With that, maybe I'll just close off with a slightly different topic, how material company can really accelerate the development when the standard example exists. So when you look at Institute of Printed Circuit that actually have some kind of standard, that is really actually making the whole value chain in terms of electrical engineer, fabricators, and material companies and be able to work together to get to the goal really fast. So example, what you see it here is USB specification as what to do in specific parameters, what is needed and what are some of the losses and conditions. And based on this one, IPC will basically set up the design standard to do how to make these types of structures and some of the parameter designs. But at the same time, they set up the material standards, what are some of the frequency and dielectric losses, and how to test what are some of the resin system, the filler concentration and such. So they set up the specification that it really helps material company like us to develop new types of different materials. It can be LCP, reinforced epoxy, polyimide, and other that meets the material standards based on the parameters. Then fabricator can combine those design and the material standards to be able to accelerate their prototype and be able to demonstrate or invalidate and to go from there. So this one is a very cohesive, a flow chart, what you see from IPC and as well as the industry and the fabricators in PCB. If you think about this co-packaged optics, the optics now coming into PCB board, how to assemble it, all different companies are actually working somewhat different proprietary type designs. You have seen from IBM, Alexander gave a few different options, and SABIC has a different types of connector design. Our company has a different types of materials we develop. But in terms of material standards, there's no specific details aligned yet. There are different companies, different emphasis on different parameters. I'm not saying that is wrong, but if we have some of the general standard, that will certainly help for as a just general industry to be able to adapt and be able to move faster. And as you can see, IEEE specification actually has the parameters in terms of optical system, IPC design standard in general, packaging and optoelectronics conditions exist, but there are still some gaps in here. And I believe the consortium like a COBO and or subgroup in CPO within COBO, if we can actually work together to set some of the material standard, not just the system level or the parameters and the unit standard, that will certainly help for the material suppliers to be able to accelerate the development that really meets the final end goal for fabricator to be able to actually build the system. With that, we strongly believe that really co-packaged optics will really drive the next generation high bandwidth switch. There's so many different material opportunity exist, and then that requires some of the novel optical or electrical or even thermal property materials. And then our company is actively working on many different fronts. Some of them it is already commercialized, in the front. Some of them are mostly on the development side as well. And then lastly, as I mentioned briefly, some of the establishment of the material standard will certainly help in terms of helping out in this optics plus packaging society to actually grow together to accelerate the growth in overall. Thank you again for listening to my talk. So I'll hand over to Jim.
All right. Thank you, Jake. That was a really great presentation. A lot of interesting ideas on the development side there. And thank you also to Peter. So this is the Q&A portion of our webinar, and everyone is welcome to submit their questions. We have a couple of them coming in already. So let's begin. So Peter, there's a couple I think that are addressed to you. The first one let's take is what's the precision that can be achieved with thermoplastics?
Yeah, so that's a great question, and it really depends on. Well, there's two main factors to it. So the first is understanding the mold tolerances are one of the key parameters there in terms of having a very well designed and well modeled mold, because what you can design down to usually is on the order of micron variances between, say, like if you're trying to space lenses, 250 microns apart, you can set specifications where you're plus or minus 1 micron on those lenses. And micromolders, we've seen capability from multiple micromolders where they can do that. The biggest consideration there, of course, is that the micromolder has to know what they're doing and how to actually build a mold to actually get to that tolerance of design, because there are ways of doing the injection molded process, like I was showing with the simulation, where you can injection mold a part and actually build in a variance just due to those like how you produce the component. But in a lot of cases, our micromolders know how to get down to that micron tolerance level.
Okay, I have another question on specifications for you. And when you were talking about the aging characteristics of thermoplastics, what is the general consensus on that? Has the expectation for like mean time between failure, I guess, of these components been changing in any way?
So the basic standards, say like the Telecordia standard or other standards like that, have always remained fixed. It's mainly that a lot of our customers want always like longer lead times. And so if the standard says 1,000 hours, they'll request 2,000, 4,000 hours. And always that's one of those things where if we don't have it, it's going to take 4,000 hours for us to get it. So if there's feedback like that, it's always the best thing to tell us is upfront, even if you're just potentially considering it, so we can get those sort of tests started.
Okay, so those expectations as to like how long these components would last, these connectors would last, that hasn't changed then? Even so,
the actual formal standard hasn't, but the informal data requests, I would say, are continuing to go to longer times. There's also sort of, thermal cycling shock tests and things like that, where it's just mainly a request of the lead time, especially in, say, telecom in certain cases, they're pushing it out to longer and longer use cycles. So in those cases, you need to make sure that the material will withstand not just 1,000 hours, but say 4,000, 5,000 hours. And as long as you can maintain that, stability and tolerance, that's what you need to really focus on as a material supplier.
Okay, great. So how are the solder reflow for better alignment of OE components being modeled? What are the various tools that you're using for modeling of solder reflow self-alignment?
So we actually, in a lot of cases, for the actual modeling itself of the before and after, we have the capability to do all of we have the components, we have PCB boards, we can do the assembly and actually run the testing, and then we measure dimensional stability or just the optical alignment throughout. The main reason we do it that way is that we really can't control designs of a customer. We can't dictate, how many lenses and where you put them, or your PCB subassembly if you're using some array of lasers that we haven't seen before. So we don't try to do the modeling. What we're really focused on is if we would give you and say, again, that dimensional tolerancing that I was showing is submicron, here's the distribution of it. In general, you can plug some of those things into, say, Optic Studio and actually get out that light signal loss as well. So it's something that we can do and translate out. It's just something that, again, our expertise is really on the material side, so we don't focus on that as much. if there are, interested companies that want to sort of collaborate with us and actually build out that second backend package, we'd be more than happy to talk to them, because it'd be interesting for me to see that response as well, just from my, perspective, more being on the material side than the optics side.
Okay, great. And your contact information was there on the slides. So the topic of next-gen polymers, also very interesting. Is there any attempt to make a housing in next-generation polymers, which could rival Kovar or ceramic as a material for a gold box, perhaps a polymer body and a copper molybdenum base?
So that's actually a fascinating question, because well, the last trade show we got to go to was Photonics West before everything shut down, and we had actually a few people at our booth that brought that up as well. So we're just starting to look into things like that. It's an interesting idea on how good of performance can you get out compared to, say, the ceramic or metal. We're sort of in the preliminary stage, so unfortunately, I can't really provide too much detail beyond that, because we're just trying to wrap our heads around how that works.
Okay, but in your presentation, when you were talking about new polymers, you said something about that there was a big interest in OLEDs, the use of new polymers for OLEDs, maybe because it was a big market?
It's so like if you're taking, say, your standard phone and want it to be a foldable phone with a plastic film on it, right? They need that whole process to go through solder reflow capability and have high transparency. So it has that same type of process alignment that we're talking about here in the data center. It's just that you need to make a 10 micron thick film that is perfectly flat. That's a bit different than, say, trying to make something where you're designing in an optical form of, say, like a lens or a reflective mirror or something like that.
Okay, all right, great. Jake, some questions for you too.
Yep.
So first, has there been an effort to build a BCP cyclotron waveguide for coupling light between a waveguide and a standard SMF28 optical fiber?
At the current stage, I think what we do it is really either the air versus refractive index matching fluid to see the material behaviors. We have not really done a very specific customization as an interface material. There are ways to adjust refractive index of the BCB material to get more closer to glass fiber, but generally the polymer material will not get as close as glass unless you actually introduce some other ways. So our approach has been still having it from glass to the polymer fiber and in between some other types of material to actually mitigate those the loss issues.
Okay, maybe drilling down even a little bit more on that, on the material design requirements for low RI optical adhesives.
Yeah, there are, I guess, the design requirement, meaning, I guess, what kind of approach is what we are taking it. I guess you can think of a few different ways. You can change the free volume space. You can introduce within the backbone structure that may end up reducing over refractive index. You may end up having some types of either voids and others that can also reduce refractive index. That's been practiced in academia and others so forth. If you're not considering some other types of filler materials as well. But details, it's maybe difficult to comment.
Okay.
Yeah.
What is the magnitude of the dimensional stability of the cured material for reflow process?
So dimensional stability, it doesn't necessarily change after 250 degrees and so forth. It actually doesn't change. TG of the, I guess, the material, BCB material, what we have is actually even above 300 degrees C. What the customers are actually looking for, or the industry is looking for, is really the optical properties after those high temperature as well. So what we see from our material is it's really stable even after very high temperature. Structure shape-wise, it stays as is. Even the reaction conditions are relatively high temperatures, but so it doesn't necessarily change, at least from the sort of reflow perspective.
Okay. What's the best way to align or decouple light between an SI waveguide and polymer waveguides with low loss?
I think it is ongoing activities from many different companies. Maybe I can refer to one of the IBM papers, Alexander actually, and others actually demonstrated so far. what they have done it was really just coupling and on top of each other, basically. So it's basically adiabatic coupling the light coming from polymer waveguide to silicon waveguide, and that was really the great demonstration. The industry actually, the leading industry actually was able to demonstrate. And same goes for silicon waveguide to polymer waveguide. If you think about it, silicon waveguide will have about the dimension of 100 nanometer and so forth. But the polymer waveguide is about range of a few microns. So the tolerance in terms of the alignment, it doesn't necessarily needs to be perfect, but still be able to adiabatically couple. So that's the general practice what I've seen from academia, at least.
Okay, a little bit more on polymer waveguides. Are they able to cross with low crosstalk? What about isolation?
Yeah. Based on, so we as a company, we have not done really the over cross system per se, but based on internal modeling with the refractive index and loss value, what we have is so far, as long as the dimension itself is further from about 15 micron or above from the cladding surroundings, it should really be able to isolate. And we were able to see from side to side, but in terms of the vertical crossing, we have not actually done the test so far.
Okay.
And we also do not know whether that will also be really system level necessary, unless you're just going with a different S band with a single layer. If you go into multi-layer, then it'll be a different story.
Okay, fantastic. Peter, are low temperature solder reflow processes under 200 C being explored to reduce CTE mismatches and general misalignment issues?
Yeah, sorry. Yeah, that is actually something that's being explored. That type of technology is also used in other sub-assemblies in certain like consumer electronics applications as well. For what we've seen from that, there's still been reliability issues, at least from what we've heard from our customers surrounding the low temperature solder, that it makes them uncomfortable to actually put it in. And the other problem has always been, as soon as you do that, that part is the weakest part on the board effectively in terms of how you have to handle the entire switch center, let's say. So that whole PCB now has to go through low temperature solder only. And that's always been one of the struggles with low temperature solder, especially if we're just integrating it onto a very small chiplet. Now that whole system has to be low temperature solder. It is something that we do know the capabilities of all of our materials for that. So it's something of, if you want a low temperature solder based material, say the 180 degrees C for some of the, I think, bismuth based ones, we do know of what resins would match up correctly in terms of thermal properties and optical properties to actually tailor it for that application. It's just something we haven't really seen a huge amount of pull for.
Okay. All right, great. So we're coming up to the top of the hour, the end of our event. This webinar will be available for playback, hopefully within a couple of days, and the slides will be posted up there. Contact information was posted there as well, so you guys will be able to see that. So just before we close, I just wanted to ask if Peter or Jake, if you had any comments for each other or questions for each other.
Not from my side. I think we have a personal email, so we can follow with more specifics. But
yeah,
it was great talking to each other. So
okay, all right.
Yeah, and I would just like to say that at least from the perspective of both of our companies, right? I think it's that we both see the same types of needs. It's just, again, the approaches are always going to be different because of the base chemistry and material science we know how to do, and it's not that any one of them is good or it always needs to match what your application desires. And that's one of the things that, there's various utilities for everything that we've done. It's just a matter of how we implement them. So I appreciate especially just seeing how other companies think, including from all these COPO talks, and I look forward to the next ones in the future.
All right. Well, thank you very much. And thank you everyone for joining us today.